Yeah.
So we're glad to have Enrico Pajer today here from Utrecht University. So Enrico got his PhD at Utrecht Maximilian University in Munich in 2008, and then he went to a postdoc in the high-energy theory group at Conformal University, and from 2011 he was a research associate at Princeton, and then went to the Institute for Theoretical Physics at Utrecht University in 2000-something. So today he will give a talk about the story of a simpler universe as well.
Okay, thank you very much for the kind introduction. So I want to say something about this story, how the universe just got simpler in the past maybe 5 to 10 years. But before starting, I do realize, yeah, maybe you didn't know, but that's why I'm telling the story. So I do realize that there is quite a big breadth of topic being covered in this institute, and so people have different background. So please help me out in pitching this talk at the right level. If I'm using things that I haven't introduced appropriately, please do ask as many questions as you can. I thought I had few slides until Dan told me that Lam just gave a talk with only 8 slides. So I guess I have a very large number of slides, maybe as many as 20. But I can go through it slowly and then make it really interesting for everyone. So this is the outline. I'll discuss. Here I'm trying to set the stage, what is the state of the art as far as understanding the cosmology of the very early universe, and I'll focus completely on inflation. So I'm going to tell you why our universe just got simple, and maybe you didn't know, maybe you haven't heard of it. And then I'm going to get into the details of what that simplicity means from a theoretical point of view. And I'll conclude. OK, so I thought I should just, although people know this very well, I need to put a couple of slides just to set the theme. And of course, the first slides that I have to put is cosmic pies. This is how the cosmic pie looks nowadays, and you're very familiar with that, the fact that we're only 5% of the energy density of the universe. But of course, in the past, it wasn't like this. If we start evolving that cosmic pie towards the past, there was a moment in which that pie looked very different, like its ingredient seemed to be, of course, as we understand very well because of the expansion of the universe, a function of time. So actually, in the past, it was mostly all matter. Earlier on, it was all light and neutrinos. And so kind of the goal of this talk, or one of the principles that we are trying to figure out, is what kind of pi was relevant in this first fraction of a second of the early universe. What were the ingredients that made up the universe? So that's kind of the goal. So pretty much everything I'm going to say will eventually regard this first fraction of a second. So let me be a little bit more specific about that. So this same story here, this is the whole history of the universe as we understand it. This is our cosmology. And let me try to make it a little bit more quantitative. This is the same plot. Is there a stick? Good, so I can gauge my distance from the slides. So the horizontal axis here is time, and we're living here some 14 billion years after the Big Bang. And the black line here represents the size of the Hubble radius as a function of time. And this, roughly speaking, you can think of it what you can observe at any given time, what is allowed to send you information. And you can see that this one has been increasing for most of the history of the universe. And these are the various phases that we discussed before: energy domination, matter domination, radiation. The red lines here are wavelengths, physical wavelength. Let's say you set up a perturbation. Since the universe is expanding, the wavelength of this perturbation grows with time. So the vertical axis is any length scale in particular. And so you can see that if you're interested in knowing how structures in the universe, large-scale structure, are organized, you need to describe the evolution of these perturbations of these wavelengths that couple to other wavelengths. But you would like to know what the initial conditions for this perturbation should be. And so you follow this red line, and you see that eventually this red line, the wavelength of this perturbation was much larger than the Hubble radius at early times. That means that if you were to stop your cosmology here, you would oblige to impose your initial condition on scales that are are causally, that are not causally connected. That's why we don't want to stop here at a fraction of a second where we think we understand how the Big Bang works, but we want to try to expand it further back. Notice that during phases of decelerated expansion, like during radiation and matter domination, the red arrows are less steep than the Hubble radius, and so perturbations enter a horizon, and the opposite happens during phases of accelerated expansion, like now. So there is the way we think we understand how to put initial condition in the universe is to assume that there was a phase of accelerated expansion earlier on, so that these perturbations can be explained causally. And all of this talk will be trying to explain what happened here and how what happened here, and I'm going to argue why I think it was inflation, set up the initial condition on this yellow surface, and those are the things that we used for the cosmic microwave background, large-scale structure simulations, and the distribution of everything in the universe. So all of the talk will be try to understand what the initial conditions are on this initial hypersurface, and to do that, I'll have to go into the details of the physics of inflation. Okay, so people always give a couple of motivations for why they like inflation. I thought I would also give a couple, but maybe slightly different from the one that I usually mention. Usually people mention the horizon problem and the curvature problem. Why is the universe so spatially flat? Why is the universe so homogeneous? I thought I would mention two different reasons why inflation is a compelling paradigm for what happened in the first fraction of a second, that are maybe less often discussed, but they are nonetheless very convincing. So first argument for why inflation took place is that, how did we learn to love inflation? Is if we look at the two-point correlation function in the sky of temperature and polarization. So you have this, of the cosmic microwave background. So you measure the temperature of photons that comes to you from different directions. You make a temperature map of the sky. And then you measure their polarization as a function of difference. You make a polarization map of the sky. You correlate these two maps. Correlation looks much better in Fourier space or spherical harmonic space. And this is what the temperature polarization correlation as measured by Planck looks like. This is 0. It means no correlation. And then you see these beautiful oscillations that we think we understand very well as consequence of the acoustic oscillation in this primordial plasma. So all this very clear physics. Actually, pretty much if you can solve an harmonic oscillator, you can understand this oscillation. The physics is as simple as that. It's very linear. What I want to draw your attention is that there is a negative correlation between temperature and polarization at scales that are now of the order of maybe 10 degrees or so. If we want to ask how large were those scales at the time in which the cosmic microwave background was released, they were much larger than the Hubble radius at that time. It means that at that time there were waves that were not evolving in a causal way, and nevertheless they knew that if it is hotter, or if you want less, or if it is colder, if you want more dense, then the velocity has to go inside. So you can think of polarization as a proxy for velocity, and as temperature as a proxy for density. And so basically the way the initial conditions were set up is that when there was an overdense place, velocity was flowing inside, and vice versa. You would think that's obvious from your gravitational intuition. If there is a dense object, things flow in. But notice that those scales didn't have any gravitational evolution at that time because they were still super Hubble in nature. So some primordial physics must have set up that negative correlation. So this is the first reason why we like inflation, because it gives a primordial explanation for the initial condition for the universe. We think that the word primordial here is necessary. So the fact that perturbations are coherent on super horizon scale. And reason number 2 is that we're going to plot the same thing, but now we only show the power spectrum of temperature with itself. So the temperature power spectrum, of course, this is a positive definite quantity, so this is the 0 axis. And we see again these beautiful acoustic oscillations, which we understand very well. The most interesting fact about this The simplest thing to capture is the fact that on very large scales, scales that were not processed by the plasma or gravitational evolution, they have an approximately scale invariant power spectrum, the same amount of power on all possible angular scales on large scales. Actually, if you were to undo all these acoustic oscillations, which you can easily do, since it's physics we think we understand very well, you would find out that all the initial conditions were scale invariant, also the one that gave rise to this. So pretty much, for some reason, we find that the universe decided to start with the same amount of power on all possible scales. This is a very remarkable way to start the universe. And what I will argue today as well is that that is a direct you can think of it as arising from the isometry of the space-time in the first fraction of a second. In particular, if the space-time was de Sitter, you can see that automatically as a consequence of the Sitter isometries, you get a scale invariant, approximately scale invariant power spectrum. So two reasons, primordial, and the geometry has to have the isometries of de Sitter, and that's why we like inflations. Some questions on that? Okay, so this is what was kind of very well known. What has become, so let me say 2 words about inflation. I have to do that. And I'm going to use the language of particle physics. So inflation is a way to explore physics beyond the standard model, and it has already given us, well, you could say 2 or 3 discoveries. One thing we have discovered is that there has to be a new degree of freedom in the standard model, which we're going to call the inflaton. We need a new scalar degree of freedom. The Higgs itself most likely cannot do it the way we understand it. Okay, so we have discovered a new particle in this sense. Discovery number 2 or 3 or 4 is that there have to be new scales in nature. New scales that do not derive from the standard model dimensionful quantities. They have to be some other dimensionful quantity that you put in the Lagrangian of the universe. One has to be the scale of inflation. So at what energy scale did this take place? So let's say the Hubble scale during this process of exponential expansion. We know this didn't last forever, so this must change with time. The rate of changing with time is another time scale that you have to put in. And for something I'll convince you in a second is that even the second derivative of the Hubble cannot be 0. So Hubble cannot evolve linearly in time. And so there has to be a second derivative acting on it. That's another scale. So we think that we have discovered in our universe 3 new scales. I always write them like this so that the parameters are dimensionless, just by dividing the time derivative by the quantity itself. So this epsilon and this eta are dimensionless. So whatever is the Lagrangian of the universe, it needs to have at least 1 or perhaps 3 new scales that explain these 3 new scales that we observe in the sky. Yes?
So why do we stop at a second derivative?
Because we haven't observed anything beyond this. Like data does not require for that, presumably exists, but we don't have a direct measurement. Well, the goal of this talk will be to say that we have a very specific measurement of this number. So this has to be explained. And it could be most likely that all of these scales are related to each other in terms of some smaller number of fundamental parameters, and that's kind of the goal of understanding one of the ways that we think about inflation. But I'm trying to set this up because I'm going to argue in a second that there is a huge difference between these 2 scales. So that will be other question. Okay, so this is still at the level of reviews. What do we measure? Well, we measure the thing that was for sure around during the early universe was gravity. And so you can measure 2-point functions, which is the simplest thing that you can do. And you either measure G mu nu is a tensor. The zero mu components are not dynamical, so we usually don't care about those. So we only look at the spatial components, ij. And you can either look at the trace, so the 2-point function of the trace that behaves like a scalar. And that has this particular form, which I'm going to call scale invariant, is 1 over k cubed. This is in Fourier space and has a certain amplitude in front that we know very well in terms of these scales that I've introduced. You see Hubble and epsilon, 2 of the scales appearing in the previous slide. And we have also measured the 2-point function of the transverse traceless component of the metric. So this is a 3 times 3 metric, so you can look at the diagonal, but you can also look at the off-diagonal terms. And those are the gravitational waves that many of you know very well. And within the context of inflation, that we also know what the power spectrum of that is, and we know the amplitude. You see, the amplitude contains, again, the same Hubble scale as before, but no epsilon. So these are our observable. This is what we get to play with. OK, let's come to what we know so far. What we know so far is that the scalar two-point function, the GII correlation function, the primordial one, is approximately scale invariant. We know its amplitude is 10 to the minus 10, so we know we can use perturbation theory. So if you want, we have measured this quantity here, h squared over epsilon. We know that number. We know it's not exactly scale invariant. You see, this is data. Actually, this is all data given by ACT plus WMAB, but we know that the power has to be slightly different. So actually, we know another number. We know that the dependence on k is not exactly k to the 3, but k to the 3 plus something. And that something is also a measured number. It's 3%. Yes?
So I'm probably jumping ahead a bit, but you're assuming here that you have single field and
Yes. Yes, very good. Yeah, I'll say that in a second. Here I'm assuming single field slow roll inflation for a reason that will become clear in a second. I'll get at the end of the slide, I'll address that. Good, so we have two measurements. And in principle, we could make other measurements like the tensor power spectrum. We haven't seen it. There has been no detection of primordial gravitational waves. So we don't know what the amplitude of the transverse traceless part is yet. We could measure the running, but we haven't measured it. Notice that there is a huge experimental effort in trying to measure the amplitude of primordial gravitational waves, which of course would be extremely exciting. What I'm trying to point out here is that the amplitude could be anywhere in this pink region here, and therefore being observable now or in the next 10 or 20 years. Or it could be as far as 50 orders of magnitude smaller, and our picture of the early universe would work in exactly the same way. So we have to be a little bit lucky that the universe decides to be here rather than anywhere else. And this is putting the least informative prior, which is a log prior on the scale of inflation. So although it's great if we discover primordial gravitational waves, it would be interesting to know what if we didn't discover them. How are we going to think about the early universe if we never see gravitational waves? And what I want to argue is that if we interpret observation within the simplest possible paradigm, which is, as Joel was pointing out, single field slow roll inflation, there is something that we learn by not observing primordial tensor modes. In fact, we have already learned something. So far, by the effort of trying to measure primordial gravitational waves through the B-mode polarization of the CMB, we have put bounds on R, which is the tensor to scalar ratio, which is the ratio between the transverse tracer's power and the trace power. So we basically know that perturbation in our universe up to 7%, they are really scalar in nature. So this bound gets better every year, and it probably will get an order of magnitude or perhaps two better in the next 20 to 30 years. And of course, one obvious thing that does is that if you plot on a certain, let's say, the tilt and the tensor to scalar ratio, as your bound gets better, you start excluding models. 5 to the 4th excluded, 5 to the square almost excluded, and if you get better and better, you start excluding more and more models. That's, of course, interesting to do. We need to exclude models, but it doesn't teach you something doesn't teach you a broader lesson. So what I want to try to argue today is that the fact that we have not discovered primordial gravitational waves actually teaches us a broad general lesson about the early universe if we assume the simplest possible model, which is single phase slow roll inflation. In particular, we know, as I told you, we have measured the tilt. The tilt is 3%, and in single phase slow roll inflation is just given by a combination of the two scales that I introduced before, epsilon and eta. But we also have not seen any tensor to scalar ratio. So we know that, which is also related to this parameter epsilon. So we know epsilon has to be smaller than 0.05, just coming from this ratio here. And so it cannot contribute very much to this 4%, right? So this 4% is pretty much only given by eta. Okay, so the most interesting thing that we have learned about the early universe in the past 10 years or so, I think, is this. We know that of the three scales that must exist in nature to explain the early universe, I told you the Hubble scale, the epsilon scale, and the eta scale, there is a hierarchy. Eta is much larger than epsilon. That's something that we know today, assuming single fields low rho. I think that's the most important thing we have learned so far. And in the absence of a detection of primordial gravitational waves, it will be the only thing we will learn in the future. So it's nice to see what that implies. Of course, when you have a new hierarchy, you can start playing all kinds of games. What does that hierarchy mean? Is it natural? What does it imply in terms of observable? And that will be the goal of the rest of the talk. Let me mention that the way I'm thinking about the primordial gravitational waves, or way to measure primordial beam modes in some sense, is either we get lucky and we see something, or we are establishing this hierarchy. So it's important to know what this hierarchy implies, because chances are this is what we are doing by trying to measure the polarization of the early universe.
But you could also have a non-trivial sound speed or multiple fields, or
Yeah. So let's write the formula with the non-trivial sound speed. I wish I had the plot. So if we have a non-trivial sound, this is maybe a little bit more technical, but I'm going to still show it. So this is, I'll just show it to you. So this is smaller than epsilon, bigger than epsilon. OK, so we have bounds from non-Gaussianity. From non-Gaussianity, we have bounds that CS cannot be very small, so we have to be on this side of the plot. And from B-mode polarizations, we know we have to be, epsilon cannot be so large, so we have to be low here. So far, there is only this little corner in which it is possible, even for a varying CS, that eta is of order of or smaller than epsilon, this corner here. The next generation of gravitation of, let's say, pixie or core will completely close off this triangle. So this would be, let's say, pixie or core. So for me, one of the goals of pixie or core is to establish the existence of this hierarchy for any speed of sound. So far, we know it only if you assume 1. If you assume 1, then eta is much bigger. If you assume speed of sound of 1, eta is much bigger than epsilon. But there is still this caveat. With pixie on core, or core, the bound will get so better, and the bound on non-Gaussianity will also increase, that basically all of this will be excluded, and you will have to be here, where eta is much bigger than epsilon. So that's my vision of why to motivate those experiments in the absence of a detection.
So what is the number on R, the horizontal one?
10 to the minus 3, yeah. And actually, there will be an improvement also on the lower bound of CS, coming from the fact that if we don't see equilateral non-Gaussianity, then CS cannot be very small. Because
Sorry, what number are you using for that?
the forecast for the latest design of the core mission that is going to be proposed for this 5th European call for a mid-class. So that there is going to be a white paper on core coming out this week, and this is the number that comes from that paper. Pretty much in the next 10 years, we're going to exclude this triangle. And I think that's important to understand that that's one of the things we're doing if we don't see anything. OK, something else?
Well, multiple fields, I guess, would still be.
Yes, so that depends on what your take is on FNL local to be smaller than or of order 5, which is our current bound. I think there are multifield models in which this exists. I'm not sure we will ever be able to rule out multifield models unless we are carefully in defining what we mean by multifield. Because the obvious definition of multifield includes single field as a subclass.
What's your take on anomalies?
On?
Anomalies.
I haven't been dedicating my time to that yet. So I didn't consider them compelling enough because they tend to be on larger scales.
But in terms of the inflationary effective potential,
they might have
they
something.
aren't very different at all in scales in terms of phi.
Oh, sorry, in terms.
Of phi, of the input on field.
Yes, yes. So they.
So you know, I mean, The issue is we don't have the best statistics.
Mhm.
If you just look at the maps, something stares at you that says that is non-Gaussian.
Oh, sorry, on non-Gaussianity. Oh, you mean the
Well,
anomaly?
it's non-Gaussian, it's also maybe associated with a feature which is wave number dependent, which isn't in this simple description of epsilon and derivatives of epsilon.
Yeah. No, I think that's an interesting question. So how much this is calling for making more complicated models? Here the philosophy is a little bit, what is our vanilla picture in which we give the simplest possible explanation of the largest possible amount of signal to noise. And then on top of that, you can try to play the game whether you have enough signal to noise to introduce a new parameter and make a more complicated model. So far, it seems that if you want to explain like a single anomaly at a time, introducing a parameter never pays off in terms of Bayesian evidence. Like typically, you introduce an anisotropic correlation between the power spectrum and a long mode to.
And all of those things are in the data. It's just a question of whether the statistics under the current theoretical framework flips you over the line or not.
Yeah,
But by the
absolutely.
same token,
Yeah.
In terms of what Joel has said, then there's the whole isocurvature aspect that's sitting below and doesn't really belong to this model.
Absolutely, yeah. There are a lot of things that we haven't seen, like isocurvature, that would go beyond this. Yeah. This is a little bit what story I'm going to tell my children in 20 years if we haven't seen non-Gaussianity and tensor modes. I'm going to tell them this is the way the early universe is. And I guess other people can have different opinion on how the universe could be. But this seems to be the most grounded, simple-minded, minimal, conservative set of assumptions. But that those are, of course, very interesting fields of research and work should be done. I'm not saying you shouldn't do that. I'm trying to be simple here and asking a little bit deeper question about the simplest model, which you would think is a boring model because they use a single field slow roll. And I'm trying to point out that there is something that has not been completely explored about that simple single field slow roll model. Okay, so I'm going to discuss about that single field. So one problem is, of course, that there are already many models, even if you restrict to single field, and more so if you have many fields. So how do you proceed? I think emphasizing the role of symmetry is always pays out in physics, and so it does here. For example, one interesting development here was understanding the role of the spontaneous breaking of time translation, and that has led to this effective field theory, a way of thinking about inflation that is not tied to the single scalar field potential. I think that the space-time isometries play an important role that had not been exploited so much, so that's what I'm going to do in this talk. And I think there is more work to do. The shift symmetry constraint on correlators, I think they're pretty much not explored. So that's something I'm aiming to do for future work, and maybe I'll leave it to the discussion if you have some questions about that. But let me tell you what we still haven't completely digested in terms of the isometries of space-times for single field slow roll inflation. So this is going to be the last part of the talk. The conformal limit of inflation. I already argued that there is a hierarchy of scales, so what does that teach us? Basically, it teaches that the CITA isometries that all primordial correlators, 2-point function, 3-point function of any perturbations in the universe, they must be the CITA isometric, or if you want, conformal invariant. I'm going to show you that these two groups are actually the same group. Something that had not been pointed out before, and this is only true in this limit. Okay, so that limit, that specifically limit, tells me that all n-point functions of our universe are the CITA invariant or conformal invariant. In particular, for the 2-point function and the 3-point function, this completely fixes the correlators. There is no free parameters. You don't even have to compute it. It's just fixed by symmetries. For higher n-point function, this is not true. And I'm going to give you also a hand-wavy way to see that using the wave functional of the universe. But this is the message. That limit tells me that there is conformal invariance of all correlators. So since I'm going to work in that limit, I have to define it a little bit more rigorously. So what do I mean by eta much smaller than epsilon? What do I keep fixed? What do I vary? So one obvious thing that you want to do is that you take epsilon to 0, right? So you make epsilon the smallest parameter in the game, so you take it to 0. We cannot take epsilon to 0 so easily because if you remember, there is a quantity which is the amplitude of the primordial power spectrum, which is 1 over epsilon. That's a measured number. So we need to be sure that this is just 10 to the minus 7 because that's measured. So if I take epsilon to 0, at the same time I have to take this dimensionless ratio h over m Planck to 0. For me, the best way to visualize what h over m Planck to 0 means is to take m Planck to infinity. And that way of thinking about it makes it clear that this limit, you are obliged to take the decoupling limit in which gravity is a fixed background. So if you put two objects there, they're not going to attract each other with Newton force. Gravity is fixed, and Planck is infinity, G Newton is 0. So whatever gravitational background you decide to have, Minkowski, de Sitter, Feller, that's it. You cannot modify it with your masses. Okay? That's what the decoupling limit is. So this is what that measurement already forces us to be in this limit. And the other thing that I'm going to assume is what Paul was pointing out. CS is equals to 1, or I'm going to exclude any cases in which the scalar field breaks de Sitter isometries by having some constant density with speed of sound different from 1. Okay, so this is some assumption. In particular, this assumption excludes CS from being different from 1. If CS, the speed of sound of perturbations was different from 1, clearly I would break the Sitter isometries because perturbations move along the sound cone while the Sitter is going to move around the light cone. Okay, so this is what makes it single field slow roll simple model. And I think that's the simplest thing we have. Okay, so in case someone is worried whether this limit exists, pretty much every model that is still compatible with data is included in this limit, as is perhaps obvious. In particular, Starobinsky models, every small field model of inflation, they all have more or less this property in which epsilon scales like the number of e-folding, like an inverse power, 1 over the number of e-foldings, and the power is like 2, for example, for Starobinsky inflation, while all the other slow roll parameters, starting with eta and higher order slow roll parameter defined by this, they all go like 1 over n. N is the number of observed of e-folding since the CMB scales left the horizon, so that's 60. So epsilon is automatically 16 times smaller than eta, or even further smaller in other models. So all single field slow roll models that work are in this class. So in that sense, I think this is an interesting thing to point out. This is something that all those models have in common. They have epsilon parametrically smaller than eta. Okay, so how do we connect to the Sitter isometry? Well, let's write down the Sitter space-time. This is the de Sitter metric written down in terms of conformal time tau. Clearly has time translations, sorry, not time translations, spatial translations, spatial rotations are obvious symmetries, but it has 4 more symmetries. One is dilations. If I multiply tau and x times any number, it simplifies up and down, so there's dilations. And there is a special conformal transformation, which is just the de Sitter version of a boost. In Minkowski, you can do a boost. In de Sitter, you can do a de Sitter boost. Same. Good, so let me put a scalar field in this background and solve its equations of motion. Since it's very simple to solve the equation of motion. So what you find is that when you can neglect gradients, this is a homogeneous scalar field, or almost homogeneous. You find that its time dependence, it's a second order differential equation, so there are only 2 time dependencies, can only be of 2 types, tau to the delta with 2 different exponents. I call it delta. Yeah, 2 different exponents. And those 2 exponents are given by this formula, some order 1 numbers. And the only interesting thing is that the mass of that field appears. That's what determines how that field evolves in time. This is what is, I don't want to be too technical, but this is what is done in ADS CFT to determine the dimension of the dual operators. That's not going to be relevant for us, but basically the time dependence is fixed by the mass, as you would expect, because the field is evolving. Okay, so what are the isometries of this space? SO4, 1, which is the isometries of de Sitter. But what I'm arguing here is that this group, you can think of it as being the conformal group in three Euclidean dimensions. It's just the same group, SO4, 1. And it acts naturally on this operator, because if you take a dilation, a space-time dilation, since we know what the time dependence is, we can just take this derivative on the time dependence and just give me a factor of delta. And this is the textbook definition of what a dilation is in the conformal group. So being in de Sitter is the same thing as considering operators that are that obeys this conformal symmetry transformation. This is perhaps this is not strictly necessary. It's just to introduce a new language to talk about the CITA isometric. I could always say the CITA isometric. I'm often going to say conformal because there is a large literature on conformal transformations, and so I can just look up all the results that people have derived for conformal theories and just apply them to inflationary correlators off the shelf. I don't need to rederive anything. So maybe, let me say it in other words. If we were to compute something in Minkowski, we would only write something which is Lorentz invariant. If we compute something in de Sitter, it's only something that is conformal invariant. That's just the equivalent. Some questions on that? Okay, so let's compute the simplest possible thing, the two-point function. And I'm going to try to argue that you don't need to write the ADM formalism, solve the constraints, compute the two-point function, et cetera, et cetera. You can just compute the two-point function in single phase low roll inflation only from symmetries. In fact, in just this one slide. Okay, it's a two-point function of, let's say, the perturbations to this scalar field, to this inflaton field. You can apply a dilations, the one we just saw in the previous slide, to this two-point function, and it has to be invariant because it's an isometry of space-time. So that automatically constrains this correlator to be 1 over k to the 3 minus 2 delta. The delta, of course, appears because the action of these dilations contains a delta. So the result will depend on delta. So this is completely fixed by dilations. And now we convert to the perturbation that actually are conserved out on super horizon scales, curvature perturbation zeta. They're given by this simple formula. And this gives me the two-point function of zeta, which is what is measured. And this quantity is just the tilt. This 2 delta is just the tilt, the ns minus 1 I was arguing before, or 1 minus ns. And indeed, this derivation reproduces the correct result because the 2 delta is nothing but eta, is the same quantity.
Except that your formula has m constant.
Oh, no, sorry. Yeah, that's.
So m run.
Yeah, it was stupid for me to call it m. Every time you see m squared, think of being this. Second derivative of v in d phi. I shouldn't have written m anywhere. It's really v double prime. This is valid for any potential. Yeah, I understand it's confusing. I'm not assuming it's a quadratic potential. The running of the mass is subleading in slow roll because you need to take more derivatives, and so it's small. Very good. So this statement, okay, so in just one slide, you derive the tilt only as a consequence of that. So notice that the epsilon is wrong. So the factor of epsilon doesn't work with this argument. That requires violations of the CITA isometries. If we ever see an epsilon, we would be the first time we measure detailed violation of this. Of course, we know it's not exactly the CITA, otherwise we wouldn't be here talking today. So we know the CITA, the epsilon is not 0, but we don't know how small it is. It could be 10 to the minus 50. Okay, so except for the epsilon term, everything else is fixed by symmetry.
So let me, and again, get your take on issues of de Sitter instability.
Oh.
So as epsilon goes to 0, you have curvature fluctuations around de Sitter that dominate, and so de Sitter gets dressed, and so it isn't really de Sitter.
No, I think it's de Sitter because of the limit that I defined is carefully keeping the power spectrum constant. So the power spectrum of zeta is constant to 10 to the minus 7. So the perturbations are always a 1 in 10 to the 10 part. So I have to take the limit in which I take the Hubble scale down as I go to the zeta.
You're saying that, and I don't just want to be correct, so that you can actually go to epsilon equals 0 along a trajectory in which the curvature is actually fixed.
Yes, yeah, well, this is the limit. Well, not all the way to 0 in the sense at some point you have to require that Hubble is less than a GeV, and that would not be viable. But if we exclude that we know the scale of inflation is a little higher, yeah, I mean, you just take this limit. This is the only quantity we have measured, right, this ratio. So I can play with the two factors in this ratio. That's what I'm doing.
Yeah, I always thought of consider as fuzzy as opposed to being as strict as people want it to be, because that's a classical thing that has no direction in time. And then whenever one's dealing with inflation, you need some kind of emergent time.
No, I agree with that. What I'm pointing out is that the fuzz of the signal is always proportional to epsilon. So
exactly, so that it's an epsilon fuzzy entity.
Exactly. So, but now in our universe, we happen to be measuring quantities that seems to be much bigger than epsilon.
Correct.
So as long as I want to describe those quantities, for example, the tilt, I never need to mention the fuzz of the signal, because it's an experimental fact, if we take single fields rule, that in our universe, that fuzz is subleading. So in that sense, this is it's an interesting statement that characterizes generally our vision of the early universe. So yeah, that's a nice way of saying it. Okay, so I told you I promised you more. 2-point function, okay, well, not a big deal. It's a short calculation anyways. I'm going to fix the 3-point function as well, just based on symmetries. Yeah, 3-point function is interesting because it at least probes the interaction in the theory. We know there are some interaction because gravity is non-linear. And Maldacena already solved this problem, so in principle I could just go home here. But we actually recomputed this, but without, not the way Maldacena does it, which is an explicit direct calculation, but we're going to rederive this result and higher order ones only based on symmetry without actually computing it. So Maldacena found this nice expression. There is a term here with the tilt and a term with an epsilon. As I said before, experimentally, the tilt is larger than epsilon, so I can forget about this. So there is only this first term that I need to focus on. And this is what is called local non-Gaussianity in particular. I want to argue that this one and its higher order brother, eta squared, are both fixed by symmetries. Yes?
There are shape informations in those different terms, right? So you project into some shapes, the first term will disappear, and then the epsilon one becomes leading.
No. This is all. Sorry.
Every possible shape, you will have a bigger contribution from the tail term, and epsilon term.
No, for single field roll inflation, this is a known function that is at most 1 in a certain normalization. It peaks in equilateral and then goes to 0 times a number which is much smaller than this number. So I think, well, okay, now between eta and epsilon is just a factor of 6. But imagine we are in the future and we know epsilon is 10 to the minus 5 or something. Yeah, well, and then this one is only bigger than. Yeah, these are comparable. The normalization of this shape and the normalization of this shape are the same. In the equilateral case, they are 1 or something. Yeah, so this is all single field rule models. Okay. Well, there is a beautiful way to derive it, and it involves 2 steps. So step number 1 is going to be, step number 1, I'm going to consider a certain limit, the squeezed limit. And step number 2, I'm going to do this I'm going to use conformal symmetry. So by adding step 1 and step 2, I'm going to fix the 3-point function entirely. So step number 1, just tell me that if I consider the 3-point function, phi, 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 and one of the 3 modes is very long, there's a long history of using this argument to try to find what the result is. When the mode phi is very long, locally you would mistake it as being a change in the background. So there's something like this. And this is the phi long and phi short. As far as the short is concerned, this phi long is just changing the background of phi by a little amount. Okay. So we know that the 3-point function is actually related to how the 2-point function of the short modes behave in the background of the long mode. And that's something I can compute just given the 2-point function, which I just showed you before. So I know the 2-point functions, like the 3-point function in this specific limit, only in this specific limit, is fixed. It's some number. Now I can use conformal invariance. I know that this 3-point function, no matter what it is phi of k1, phi of k2, phi of k3. This has to be a function that is conformal invariant as a function of k1, k2, k3. Now, people worked out conformal endpoint function already 40 years ago, and that was the beginning of this big field of conformal field theories. They always work in real space. When you work in Fourier space, it's a little bit more complicated. So instead of having the beautiful Polyakov formula, which is just half a line, you have a nasty triple K integral where K are Hankel function of some type. So it's a little bit nasty, but it's a formula, it's a known thing. The most general function, which is conformal invariant, is known. So I can take that function, and that function has one free coefficient, which is the overall multiplication. That coefficient is fixed by what I just did in the previous slide. In a certain limit, I know what it is, so that fixes the coefficient. That fixes the entire three-point function. So that's what we did in our paper, and this is the result. The leading term is exactly what Maldacena had, eta times local. We found two new things. One, that there is a subleading with higher order, and we found that there is another part that I generically call equilateral, but perhaps I should call it conformal. So this is a specific shape that has the property of being conformal invariant. Okay, so I think this is interesting. The three-point function completely fixed, only because of eta much bigger than epsilon. This in particular highlights certain properties. For example, the fact that when I take epsilon to 0, the leading equilateral term is fixed by this specific combination that is nothing but the running of the power spectrum. So there is a consistency relation also in the scalar sector that relates non-Gaussianity to the tilt. I could go on and do this for hours, but that's probably not so interesting. This is valid for all endpoint function, but from the 4-point function onward is not enough information to completely fix it.
If you have no higher order derivatives, then psi is 0?
No, psi could be non-zero. Psi is just eta dot over eta Hubble, and in typical models, this is of order of 1 over the number of E-foldings. For example, let's say Starobinsky has a stereotypical model, a model that looks like this, and you're here and you inflate down, then psi is 1 over n.
But for constant mass, there's no effect. It is 0. If I just define something where there is no effect.
No, I think for constant mass, I think it's still 1 over. I think it's still 1 over n.
It's not only the mass of the potential, it's the derivative of the...
Yeah. Where is that? Yeah, it's a little bit more complicated. It's really the second derivative of Hubble. So it's not just v double prime over v and then you take a derivative. It's a bit more complicated. No, also for m square phi square, which is kind of ruled out of the data, but it would be 1 over n in that case as well. We can do the algebra before. Okay, well, this is the story. I'm out of time, right? Yeah, I think this is the story. There is another way of seeing the same story using the wave functional of the universe. But my feeling is that maybe that's, if someone wants really to see it, I'm going to show it. Otherwise, I'm just going to come to my conclusions. It's just one slide. This is the wave function of the universe. Boom. That was, you saw it happening. Okay, these are, I mean, if someone wants to see it, I can go through it. This is the story. I solved it 1 million times. It's kind of hard to test, but I think this is what I've learned by not-seeing primordial beam modes in the CMB. All endpoint functions are de Sitter invariants, assuming this simple paradigm that CS is 1 or of order 1. There is a new consistency relation. There is an equilateral non-Gaussianity, which is of the order of the running. Both of those things are extremely hard to test experimentally because the running is very small and the non-Gaussianity of that order is tiny. But there is a physical relation. Perhaps this has some application in conformal field theories that could use similar techniques. But yeah, thank you very much for listening. Yes?
If I counted correctly, by consistency relationship, you're saying that if we were to measure alpha as a running and be able to measure that bispectrum equilateral at this would correspond to f and the equilateral at 10⁻⁴ or something.
Yeah.
So if you both measured f and n at 10⁻⁴ and measured that thing, then you would have a test.
Of single field slow roll inflation. Yeah, exactly. It is, if you want, usually people say that the test of single fields low roll inflation, I can tell you why I'm stressing that. Usually people say that the test of single fields low roll is, what is it, R equals NT over 8, or there is a formula like that. Now, the problem with this is that this requires measuring the tensor sector. Is a single. If you never see the tensor sector, you don't see it. The question is there something in the scalar sector that has the same power? This is the formula. Is FNL equilateral, and we put some order 1 factors. This is in the scalar sector. It's hard to test. I don't think we will do it, but it might be 50 orders of magnitude easier to test than this. That's yes.
So I want to put this in somewhat more concrete terms, which I would like you to then give the conformal aspect to it. So there is this history of flattening potentials. And when at least some people thought there was a bicep discovery, they said we're going back to these unflattened things. But there's been this history, the way we like to do it was by a conformal transformation to do the flattening. That's an easy way to do it, and then that's Stravinsky, that's Higgs inflation, and it leads to nice properties. And what I'm trying to get at is that you have this very small amount of potential surface information that we're actually getting from the observables. But then there's the elephant in the room, which is that there has to be heating. Yep. And the heating means that epsilon goes from nearly 0 to 1.
Yep.
And so a theory is not a complete theory with that path, and that path is actually an important path. First of all, you want to look for observables associated with that path, non-trivial, but you do want to do it. But one aspect, and there's alpha attractors, all sorts of names for this now, conformal makes one think that a conformal transformation is an important way of looking at the system. But there are other ways, for example, in string-motivated inflaton potentials to get that flattening.
Yeah, yeah.
And so what I would want to try and get a handle on, if the use of the word conformal here is saying that, therefore, that kind of conformal Jordan-Grant-Sticky transformation framework is then relatively fundamental, because you were going to the limit where in which you have effectively a Planck mass, which is becoming an irrelevancy, and that's what you were using this as the limit to get to, right? And that speaks to a conformal transformation with very specific properties in terms of how that behavior might go as you go back to time.
Yeah.
And I like this model very much, not just because we worked on it, but because it has the ability of saying that when that tight coupling that keeps the gravitational field coupling small, it suppresses all of the higher order interactions, for example, the standard model. And then as that lets up, then standard models or some other model starts to kick in, and that's when the heating occurs. So in other words, I'm going back to my original question. There's a total framework here, and an interesting question is whether the way you're trying to look at it, how it actually fits into that story.
Yeah, no, I totally agree. So well, my way to at least think about your question is that this is some phenomenological observation, but I have some UV. So how do I go from the UV to generate this hierarchy? And you're saying one way of doing it is to use this conformal transformation. And I think that there are maybe a list of other ways of doing it, like string theories with flattening of stories. And I think that's definitely an interesting way to do, because this to me starts growing as a convincing fact that we have to live with, and so we want to understand what are the convincing way to get there. I would like to get there also, what I'm trying to now explore is that my difficulty with this is that there are many possibilities. And it's hard to know which one, because once you get here, everyone agrees with data in the same way. So the other way that I'm trying to go from the UV is trying to understand the effect of a shift symmetry. So this is kind of using the language of the EFT of inflation. There we are just using the breaking of time translation. We're saying that says everything that there is to say, but actually that's not true. In the EFT of inflation, you end up writing down a Lagrangian in which you have a function of times that depends on the perturbations in this way, and you never know how this time dependence is. Of course, this time dependence is exactly what we're talking about. Is this time dependence linear or quadratic? So this notion here has to do with how Hubble depends on time, and therefore how it depends on perturbations. And I think that the notion of a shift symmetry for any of these fields, shift symmetry being the potential gets flat, is what constrains this time dependence. So the vision that I have is that by appropriately defining an EFT of inflation that not only non-linearly realizes time shifts, but also non-linearly realizes shifts of the field, I would be able to generically characterize this hierarchy. And then I'm going to look for kind of what are the UV models that do that most appropriately.
So essentially you're building in the axion as a fundamental aspect of this
Exactly.
story as well as
Yeah, because when you do it in the effective field theory of inflation, you say the word axions only when you want to neglect this. You just say this one is constant. But you only say the words. You never really know linearly realize that symmetry the way that we know how to write phenomenological Lagrangians. I think that should be done. Because when we do the model building, the fact that it's an axion is like an important thing of how we do it. But then we do the EFT of inflation, and all of a sudden we almost forget about it, except for saying all time dependencies are constant. I think that there is more to say about that. And I think that will be maybe more the effective field theory counterpart of what you were discussing. But of course, both of these should be done. I'm just worried that on this side, there's so few numbers that I can play with to convince myself what's true. But I think it's the same approach. Now that we convince ourselves about this, is how do we get this from the UV? So that, I think that's the way to go forward.